Hey, hello everyone, welcome to my channel. So in this question we are going to consider the past paper May 2025 Analysis and Approaches high-level course. This is question number 8 related to mathematical induction, and in part A we have to show that 1 plus logarithm n base 2 more than logarithm n plus 1 in base 2 for positive integers, right? Okay, so now let's have a look. I just copied, and now how to prove it, how to show that the left side is more or equal than the right side. First of all, let's use this property that 1 could be represented as logarithm 2 in base 2. Okay, so now let's plug. So we're going to show that logarithm 2 in base 2 plus logarithm n in base 2 more or equal than logarithm n plus 1. Okay, so now using the property of logarithm, we can say that logarithm of 2n in base 2 more or equal than logarithm n plus 1. So if so, we can say that 2n more or equal than n plus 1, right? So this is a question so far. Is it true or not? How to understand? So first of all, we should remember that n related belongs to the positive integers. So it means that for any positive integer n, this inequality is true. So that's why that's how we have shown. Okay, so this with 2 marks. So 2 marks is yours. And now let's put this right in somewhere here on the right side. And our main focus is part B. Yeah, it's 5 marks, and it says use mathematical induction and the result from part A to prove that Simon's claim is valid. Well, the Simon's claim is this one. Okay, so we have to prove that this claim is valid. This inequality is true. Okay, let's do that. So n more logarithm n in base 2 for n positive integers. Okay, let's start to prove. Since it's math induction, we will start with the basis n is equal to 1. So and it's 1 more than logarithm 1 in base 2. Okay, logarithm 1 in base 2. So this is equal to 0, right? So 1 is more than 0. So it is true. Okay. Now, second step. B. Second step, n is equal to k. So we are supposed that it is also true for n is equal to k. So we can say that k is more than logarithm k in base 2. So let's suppose that it is true. We suppose it is true for n is equal to k. And now the main step, inductive step, n is equal to k plus 1. Okay, here we have to show that k plus 1 is more than logarithm k plus 1 in base 2. Okay, so now it's our focus. It says that from part A, result from part A, right? From part A. So we have to use part A. If we will look at the part A, we will see that we have proven that this inequality is true. Okay, and now what to do next? We can say that k plus since k plus 1 is more than logarithm logarithm k in base 2 plus 1. Okay, k plus 1. Okay, now we are going to use this. To show that it is true for n is equal to k plus 1. Okay, so how to define that it is true? Yeah, how we actually did it? It's from the part this part, right? So if we will use this part, and let me delete it first. Yeah, so if we will use this part, k more than logarithm k in base 2, and then add 1, both sides 1, our inequality stays the same, right? So that's how we used the previous step. Okay, and now from the part A we can say that this part is more than this part. Look, so now let's connect. You see, so we can continue. So I can continue this inequality and say that it is more or equal than logarithm k plus 1 in base 2, right? And now we have to connect. So we have to prove that this is true. This is true, right? And if you will connect the starting point and the finishing point, so starting point with finishing point, it is really true. Okay, so that's how we proved. So we can say that k plus 1 more, or actually more, yeah, logarithm k plus 1 in base 2. Okay, and the last sentence, thus we can say we can refer to the initial inequality n more than logarithm n in base 2. Now it's done, proved. Okay, thank you for watching. Write your comments and reaction, and see you in the next video. Goodbye.